Hello, students. Welcome to Fatigue Analysis. I'm Dr. Stewart. Today, we're going to do another example for multi-axial fatigue loading. This is example 2, and this is a fairly complicated example, so it's going to take us some time to get through it. In this example, a rotating shaft made of steel tubing with a through hole is given. We're asked to find the factor of safety against yielding and fatigue failure, given that the material is AISI 1018 cold drawn steel and that the tube's geometry and loading is as follows. So we're given the schematic here. We can see that we have a hollow tube. It has a through hole that's going through it with a diameter of 6 millimeters. The tube's inner diameter is 34 millimeters and its outer diameter is 42 millimeters. And it is subjected to a torsional load. So the red arrow indicates a torsional load at 120 newtons times meters, and a bending load. The yellow arrows indicate the bending load of 150 newtons times meters, and both of these loads are fully reversed. So these are fatigue loads that are fully reversed, and the phase in between them is 0. So they are in phase with each other. Now that we've kind of analyzed this problem, we can see that, hey, there's a lot of complicating factors here. We've got, in essence, a notch in the structure. We have multi-axial loading where we have both torsion and bending. It's in phase, it's fully reversed, so we've got some work to do. Let's start with breaking out what our knowns and unknowns are. If we check the appendix of our textbook, we'll be able to find the yield strength and the ultimate tensile strength for that 1018 cold drawn steel, where the yield strength is 370 megapascal and the ultimate tensile strength is 440 megapascal. In terms of the loading, let's define capital T as the torque and set that equal to 120 newtons times meter, and the bending moment as capital M at 150 newtons times meter. Let's also define the geometry, where big D is the outer diameter at 42 millimeters, little d is the inner diameter at 34 millimeters, and A is the diameter of our through hole at 6 millimeters. And this through hole, it represents a notch. Now let's list out what our unknowns are for this problem, and there are quite a few unknowns. First, there's what we'll define as SEP, which is the unmodified endurance limit. Then there are the CIs, which are the Marin factors. Then there's the modified endurance limit, SE. After that, we need to find how to deal with the notch. So we'll start with finding KT and KT shear, which are the static stress concentration factors. Then we'll find Q and Q shear, which are the notch sensitivity factors. And finally, KF and KF shear, which are the fatigue stress concentration factors. Next, we're going to need to calculate the stress amplitude at the stress concentration. So we're going to want to get the normal stress amplitude, sigma A, as well as the shear stress amplitude, tau A. Once we have these two amplitudes, we'll then want to apply von Mises effective stress to get an equivalent or effective stress amplitude, as well as effective mean stress, which we'll actually find is equal to 0 due to us having a fully reversed problem. So this one is actually a known. So you can see we've got a lot of steps to take in solving this problem, but there's also some assumptions that we're going to need to make that are going to affect our results. Truly, when we do fatigue analysis, sometimes our answers are subjective, and one person can get a slightly different, or it could even be a greatly different answer from another person. This comes down to the way that we read our charts. So here we're going to list what our assumptions are. For finding the stress concentration factors, we're going to use the charts. We're going to graphically plot up and over. So the answer we're going to get is subjective, and it's going to vary from person to person. Some people will say, oh, it would be a little bit more conservative than others. So we'll say that as a point of subjectivity. Next, we're going to apply Nueber's approach for estimating Q and Q shear. And using Nueber's approach, there is also some level of subjectivity in how we actually end up calculating the Q and the Q shear. How do we get the square root of rho parameter? And then lastly, we're going to apply distortion energy, i.e. the von Mises effective stress equation. There are many different effective stresses that we could have chosen. But in this case, we want to use von Mises because we've got a ductile material, and von Mises works well for ductile behaving materials. So now let's work through the solutions. We're actually going to go in the same order of our unknowns. We're going to start with finding the unmodified endurance limit, calculating the Marin factors, and determining the modified endurance limit. The unmodified endurance limit can be found using the following inequality, where it's 1/2 of the tensile strength if the tensile strength is less than 1400 megapascal, and it's 1400 megapascal otherwise. So if the tensile strength is greater than 1400, we set it equal to 1400. In our case, our tensile strength is much lower than 1400, so we find the unmodified endurance limit at 220 megapascal. Now let's go into working and finding our Marin factors. Let's start with trying to find the size factor. And in our case, our part is hollow. And so there's some questions about, with a hollow part, how we would find the Marin factor for size. What we'll do is we'll check Shigley's mechanical design book, which has a lot of the fatigue design equations. And in that book, we find that we can use an effective diameter and size factor equation to figure out what that Marin factor is, where the effective diameter for a hollow part would be 0.37 times the outside diameter. So we find our effective diameter is 15.54 millimeters, and then we can plug that in to the proper sizing function that exists, where that 15 millimeters exists. And so we pull the size function from Shigley's, and we find that the C size factor is 0.927 using the Shigley's equation. But we also have another equation from our notes in the class, from our actual lecture notes, that is slightly different. It has a slightly different structure. And with that one, we find a size of 0.911. So the question becomes, which of these two should we use? We will use the more conservative number, meaning the number that is smaller, that's going to reduce our endurance limit the most. It's going to have the most impact on the endurance limit. So we'll choose the second one. So our C size is going to be 0.911. However, if you chose the other one, if you went with the Shigley's equation, that's just another option. So again, this is where some of the subjectivity in our answers comes into play. All right, the next factor we're going to deal with is the surface factor. For our material, our material is cold drawn. So what we'll do is we'll go in the notes and we'll look in the table to see what kind of material properties, coefficients and exponents are for cold drawn. We put those in, and then we calculate our surface factor equal to 0.899. The next factor we're going to calculate is our load factor. In this case, because we have multiaxial loading, we're going to set our load factor equal to 1. So we're just going to basically disable it. And what we'll do is we'll account for the multiaxial loading case later by using the von Mises effective stress. So we're going to use that von Mises stress to deal with the influence of the multiaxial loading rather than the C load parameter. Now, there are other Marin factors that we could include, things such as temperature, things such as reliability, but in the problem statement, we're not given any information about those additional factors. So we're just going to set those remaining factors to 1, and then we're going to calculate our modified endurance limit, where C size times C serve times C load times the unmodified endurance limit gives us our modified endurance limit at 180 megapascal. So we finished step 1. Now let's move into step 2, which is finding our static stress concentration factors, KT and KT shear. What we'll do, since our textbook does not have a chart for a hollow tube with a through hole, is we will consult Shigley's mechanical design book. We'll look in the appendix and obtain the SCF charts for a hollow tube. The first one we encounter is the chart for a hollow tube that is subjected to bending, which is in table A16. Which is table A16. In that chart, we find that there are 2 dimensional ratios of interest. One is the through hole diameter over the outer diameter of our hollow tube. The other is the inner diameter of our hollow tube over the outer diameter of the hollow tube. With these 2 ratios, we can approximate from the table that KT is about 2.366. Now, again, answers will vary because this is a little bit subjective. You need to basically do like a linear approximation across this table in order to predict what your KT is going to be. So I wouldn't be surprised if there's some plus minus to everyone's answer on this KT. Next, we want to look at the hollow tube. So the SCF chart for a hollow tube subjected to torsion, because we also have this tube subjected to torsion. We're going to look in that table. It will have the same dimensional ratios as the previous one, these 2 dimensional ratios that we need to use. And then we'll do a linear approximation and find KT shear is approximately 3.5, right? And then again, answers will vary. They're subjective to a certain extent. Now that we've got our static factors, let's find our notch sensitivity factors. We decided that we would use Nueber's approach, where the notch sensitivity is equal to 1 divided by 1 plus the square root of rho over the square root of r, where r is the radius of our notch, right? Well, that square root of rho term, that is a characteristic length parameter that we need to find. Now, our textbook does not have an expression for the characteristic length rho shear, for the rho shear characteristic length. So let's use Shigley's expression instead. We're going to go to Shigley's and find the expressions. And we find the square root of rho expression in terms of the ultimate tensile strength of the material, and the square root of the shear rho term is also a function of the ultimate tensile strength of the material. So we program these in, and now we know what those square root terms are. Now let's calculate the radius of our notch. I think we've got a little typo here. The radius, so when we're doing this notch sensitivity factor, r is the radius of our notch. And so r should be a divided by 2. So that will give us the radius of the through hole. And then from that, we can get our notch sensitivity factor Q at 0.768 and the Q shear at 0.815. All right. So now that we've got our notch sensitivity factors, let's then calculate our fatigue stress concentration factors, KF and KF shear. KF, it can be directly calculated as 1 plus Q times in brackets KT minus 1. That gives us KF equal to 2.212. And KF shear has an analogous equation to that, which gets us 3.283. So these are the fatigue stress concentration factors in tension and in shear or torsion. Now, let's determine the stress amplitudes, both the normal stress amplitude and shear stress amplitude at the stress concentration, right? Now, for simplicity, let's assume that the net stress in the vicinity of the hole, so the stress in the vicinity of the hole, is going to be equal to the remote stress that we would calculate. We're doing this because otherwise we would have to subtract the area that represents the hole in order to get that net stress calculation. So we're just going to simplify it. We're going to assume that the values aren't too different, that in the vicinity of the notch versus remotely. And so the normal stress amplitude is going to be equal to the stress concentration, the fatigue stress concentration factor Kf, times the calculation for stress, for bending stress. And here we've got everything in there. So we've got the polar moment of inertia and all that stuff is kind of calculated. I mean, the area moment of inertia is calculated inside of here. So we have 32 times the bending moment times the outer diameter divided by pi times the outer diameter to the power 4 minus the inner diameter to the power 4. When we do this, our normal stress amplitude is equal to about 80 megapascal. Now let's do the calculation for the shear stress amplitude, which is going to be Kf shear times the shear stress that would develop due to torsion, which is 16 times torque times the outer diameter divided by pi times outer diameter to the power 4 minus inner diameter to the power 4, which gives us the shear stress amplitude of 47 megapascal. Now that we have the normal stress and the shear stress amplitudes, we need to take those two stresses and find a single equivalent stress. So we're going to apply von Mises stress equation. We're going to take the full form of that equation and we're going to replace sigma x with sigma a, which is the normal stress, and we're going to replace tau xy with tau a, which is the shear stress. And all of the other stress terms we're going to set equal to 0. When we do that, we find that the von Mises stress amplitude is equal to 106 megapascal. And then we also know that the mean stress is going to be equal to 0 because we are doing fully reversed loading, right? So mean stress is going to be equal to 0. Now that we have this equivalent stress amplitude, we can finally go about getting down and solving this problem. We're going to apply the modified Goodman approach in order to look and predict yielding as well as predict the factor of safety for fatigue failure. In modified Goodman, the stress amplitude divided by the endurance limit, the modified endurance limit, plus the mean stress divided by the ultimate tensile strength should be equal to 1. That is modified Goodman's approach. And if we want to introduce a safety factor, we would take that 1 and we would divide it by n, where n is a safety factor. For yielding, we can simplify modified Goodman by replacing SE and SU with SY and rearranging and solving our equation. Now, luckily, since the mean stress is equal to 0, our equation becomes much simpler. And so the safety factor for yielding is equal to the yield strength divided by our von Mises stress amplitude. So the safety factor to yielding is 3.227. Since that factor is greater than 1, the tube will not yield. We do not expect yielding to occur. All right, now let's do the fatigue case. For fatigue, the Goodman equation simplifies into the following case, where we keep SE and SU, but the mean stress is equal to 0, so we get this simple equation. We rearrange and solve. N fatigue is equal to the modified endurance limit divided by the von Mises stress amplitude. We find that it's equal to 1.571. Since that factor is greater than 1, the tube will not experience fatigue failure. And so we have solved this problem. It took a lot of steps, and we basically used almost all the skills that we've learned in fatigue analysis. But By following a systematic approach, we were able to solve this problem. In our next example, we're going to continue from where we left off and do a slight tweak to this problem and see how these safety factors change. So make sure to hit the subscribe button and hit the bell, and I will see you in the very next example video.